Welcome to the unit on gravitational forces and fields. This is lesson 28. We're going to start off by talking about the difference between weight and mass. And this is something that our hero, Sir Isaac Newton, talked about. And the basics of this are that although we commonly say, I weigh this many pounds or I weigh this many kilograms, that is, in physics terminology, that's incorrect, because what you're describing is your mass. Your weight is the force of gravity acting on you, and that will change depending on where you are. You weigh less on the moon than you do on Earth because the moon has a weaker gravitational field strength, and so the moon pulls down on you less than the Earth. Whereas your mass is the amount of atoms that your body is made up of, and that does not change depending on your location. So you have the same mass on the moon and on the Earth and on Mars and any other planetary object. So your weight changes according to where you are, but your mass doesn't unless you lose weight or cut your arm off or do something that's hopefully less dramatic. All right, so you can read over the notes here. It talks a little about inertial mass. Inertial mass is it just means mass, so don't get caught up in the terminology there. Example 1 says I have a 5-kilogram rock. Determine how much it weighs on the Earth and on the moon. Here's our formula. Our formula is question A. So our formula, let's do the Earth first. And our formula for weight is the same as the force of gravity. So it's Fg. The force of gravity equals the mass times the gravitational field strength or acceleration due to gravity. On Earth, that number is 9.81. I guess we can put the negative in there, meters per second squared. So you multiply those numbers together and you get an answer of 49.1 newtons. So that's the weight of the rock on Earth. On the moon, on the moon is much smaller, has a weaker gravitational field strength. Acceleration due to gravity on the moon is much slower. And therefore, when we plug in our G value, we use this number. You don't need to memorize that number. That's that's acceleration due to gravity on the moon. It's 1.67, so it's about 1/6 that of Earth, and you end up getting 8.35 newtons. So as you can see, the weight of the rock is different on Earth and on the moon. B says determine its mass on the Earth and the moon, and that's pretty straightforward because the answer very simply is 5.0 kilograms for both. No matter where you go in the universe, that rock will be 5 kilograms of mass because that's the amount of molecules or atoms or however you want to express that the object has. So that doesn't change. On to the second example number 4 says an object is accelerated at 3.24 meters per second squared by a 6.72 times 10 to the 4 Newton force. Determine its inertial mass. So the question is really just asking what is the mass of this object. It's a pretty straightforward one. Our formula on our formula sheet looks like this. Remember, that's just this. We commonly see it in this form here, but on your formula sheet, it appears in this form here. And we're determining the mass. Therefore, the mass equals F net over A, which is going to be 6.27 times 10 to the 4 divided by the acceleration 3.24, and you end up getting an answer of 2.07 times 10 to the 4th kilograms. All right, so pretty straightforward question there. The next concept is gravitational fields, and this is just the one where I'll just talk and explain what are gravitational fields. They're very simply any object that has mass creates a gravitational field around it. And gravitational fields, the direction of gravitational fields are always towards the center of the object. So here's our Rice Krispie box, and you can see always going towards the center of the object. When you do physics 30, you will find out that electrical fields can be either towards the object or away from the object. Same with magnetic fields. But gravitational fields are always towards the center of the object. And then we discussed this concept of test mass, which is kind of important. Test mass, so if we want to test the gravitational field strength of an object, the best thing to do is put another object close to it and see how it reacts. And we call that a test mass. Now, since any mass creates its own gravitational field, then our readings are going to be somewhat inaccurate because that gravitational field will interact with the other gravitational field, so we don't really know if we're getting the exact answer. So we create this theoretical thing, and the test mass has a mass of 1 over infinity. And 1 over infinity is an extremely small number. It's so small, it's actually insignificant. And so that's the theory behind testing the gravitational field strength of any given mass. We place a test mass with an infinitely small mass around it and measure its and see how it reacts. Now, of course, you can't do that in real life, right? But that's the theory behind it. Here is a formula for, so we've taken now our gravitational or our formula for weight or force of gravity, and we've rearranged it right here. So we've taken this formula here, and we've rearranged it for G, and we get this interesting formula right here, G, which equals Fg over m. And we know in previous lessons, we've always measured G in meters per second squared. But you can see from this rearranging this formula, you can also measure it in newtons per kilogram. Newtons per kilogram. And therefore, logically, newtons per kilogram, a newton per kilogram must equal a meter per second squared, which seems pretty odd, but it's quite true, isn't it? Because a newton, let's say this, here's a newton, and what are newtons really? Newtons are not a fundamental unit. So F equals MA, newtons equals kilograms times meters per second squared. So there are the fundamental units of what a newton is, and if I take this and plug it in over here, what do I get? Oops. Kilograms meters per second squared over kilograms equals meters per second squared. As you can see, those cancel out, and I actually get meters per second squared equals meters per second squared. So that's just a little proof of why a newton per kilogram is the same as meters per second squared. They're the same thing. One we commonly call acceleration. The other one we're now going to call gravitational field strength. Okay, and blah, 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 blah. You'll probably see the value listed near Earth's surface is 8.91 and meters per second squared and 9.81 meters per second squared and 9.81 newtons per kilogram. The two ideas are used pretty interchangeably in most questions. Okay, now we go on to this concept. This is the last concept which will lead us to the next lesson, and that is, what is the gravitational field strength in relationship to the distance? And this is the answer right here. This should be written as G is directly proportional to 1 over r squared, or it could also say that G is inversely proportional to r squared. What does that mean? It means that as you move away from the object, the gravitational field strength gets weaker in an exponential way. So, for example, if here's the Earth, if I'm standing on top of the Earth right here, and the gravitational field strength is, let's say, 1, and then I move to a position, so I'm 1 radius away from the center of the Earth, and then I move to a position that is now 2 radiuses 2 radiuses from the center of the Earth, what will my new gravitational field strength? It won't be half. It'll actually be 1 over 2 squared, which is a quarter. So if I double the distance, the gravitational field strength is a quarter. If I triple the distance, the gravitational field strength is now going to be 1/9. So that's an inverse square relationship. In other words, the further I get away from the object, gravity is less, but it's less on an exponential scale. Okay, so I hope that that's clear. That's going to become a very important concept for our next lesson on Newton's gravitational or law of universal gravitation. And that'll be coming up next. Farewell.